Okay, we're going to begin the last section in the course, which is 5.4. So I mentioned in section 5.1 that there's actually 4 methods for solving a system. You guys have seen 3 out of the 4 so far. And they are the graphing method, the substitution method, the addition method or the elimination method, and then the 4th method is to use matrices. Okay, now a matrix, or sometimes we call it a coefficient matrix, is just a table of numbers arranged in rows and columns. The plural of matrix is matrices. Okay, so suppose that I have a matrix, okay, and I'm going to call that matrix A. Usually we use capital letters to denote matrices, like A, B, C, X, Y, Z, you know. Although you can call a matrix anything you want, but usually you'll see them represented by capital letters though. Okay, and so matrix A is given by the matrix 7, 1, -2, and 13. Okay, we use square brackets to enclose the matrix, or you could use rounded brackets also. Either way is fine. Okay, just make sure that you're using brackets or parentheses to enclose all the numbers. Okay. Now, one of the things that we care about is the size of a matrix. The size of a matrix is characterized by 2 things. It's the number of rows by the number of columns, and it has to be in that order. Okay, so matrix A would be, there's 2 rows and there's 2 columns, so this would be a 2 by 2 matrix. Okay, let's take a look at these matrices here, matrix B, matrix C, and matrix D, and let's identify the size of these matrices. Okay, so here's matrix B. Again, I need to identify the number of rows by the number of columns, and it has to be in that order. Okay, so with this matrix, there's 3 rows and there's 2 columns. So this would be a 3 by 2 matrix. Matrix C, there's 2 rows and there's 3 columns. Okay, so this would be a 2 by 3 matrix. And then matrix D is there's 1 row and there's 2 columns, so this would be a 1 by 2 matrix. Okay, why do we have matrices? Well, the whole chapter is representing, you know, how to solve a system. Okay, an augmented matrix can be used to represent a system of linear equations. Okay, so let's take a look at these 2 examples next. I suppose I have a system, and we'll write each system as an augmented matrix. Okay, so what if I had the system of equations 7x plus y equal -6, and then -2x plus 13y equal 5? Right, that is an augmented matrix. Okay, so I have 2 equations. That means I'm going to have 2 rows. And I have 2 variables. Now I'm going to have 3 columns though, right? I got the x column, I got the y column, and then I have the coefficient column. So the top row is going to be, now I'm just picking off the numbers that I see in front of each coefficient there. So I got a 7 in front of x, a 1 in front of y, and then -6 in the coefficient column. In the second row, I got a -2 in front of x, a 13 in front of y, and then a 5 in the coefficient column. Okay, now notice that a coefficient matrix and an augmented matrix are different. Okay, in an augmented matrix, see this vertical bar here? That's a necessary thing that we must have. Okay, the vertical bar represents an equal sign. And with an augmented matrix, you're representing equations. In a regular matrix is just a table of numbers. It doesn't have any direct connection to equations or something like that. Okay, so there is a difference between a matrix and an augmented matrix. Okay, How about what if I wanted to represent this system as an augmented matrix? Okay, so again, I'm just picking off the coefficients in front of the variables. So in the top row, I have a 1 in front of x, a 3 in front of y, a 2 in front of z, and then a -1 on the coefficient side. In row 2, I got a 2 in front of x, a 5 in front of y, a -1 in front of z, and then a 2 on the coefficient side. Okay, and then row 3, I have a 3 in front of x, a -8 in front of y. Now I don't have any z's, right? So this equation is unsimplified. We'd have to subtract 4 from both sides. So plus 0 times z equals -7. Okay, so -7 would be on the coefficient side and 0 would be in the z column there. Okay, make sure that you got the vertical bar representing the equal signs. Okay, in an augmented matrix, we don't write equal signs. We just use the vertical bar to represent that. Okay, and now let's take a look at representing an augmented matrix as a system of linear equations. Okay, so let's see the directions here in these two examples. So what if I had the augmented matrix given by 5, -3, 4 for row 1, and then -1, 4/3, and -6 for row 2. Write that as a system. So I'm going to have two variables, right? I call them x and y. I got a 5 in front of x, a -3 in front of y equals 4. That'd be the top equation. And then the bottom equation, -x plus 4/3 y equals -6. Okay, so that'd be my answer there. How about this example next? So what if I had this augmented matrix, and let's represent it as a system. So I'm going to have 3 equations, and there's 3 unknowns, right, which I'll call x, y, and z. In the top equation, there's a 2 in front of x, a -7 in front of y, a -1 in front of z, and then equals 0 on the coefficient side. In the second equation, let's see, I'm going to have 3y plus z equals -1. And then in the bottom equation, the third equation there, I'm going to have -5x plus 9z equals 3. Okay, and so that'd be the answer. Okay. So we're going to have to know how to convert back and forth between a system to an augmented matrix and an augmented matrix to a system. Okay. Now there are 3 basic operations that you can do with a matrix. Okay. Item 1 says that you can switch any two rows that you want. Okay. So if I view this as a system, you know, I can switch any 2 equations, right? Like nobody's keeping track of the order of the equations. So because I can switch the equations, I can switch any rows in a matrix. Item 2 says that you can replace a row by a non-zero multiple of that row. So, you know, viewing this as a system, like I can multiply both sides of this equation by a number, you know, as long as it's not 0, because 0 equals 0. But I can multiply it by any number, and because I can do that with a system, I can do that with a matrix. Okay. Item 3 says that you can replace a row by the sum or difference, if you're subtracting, of that row and a non-zero multiple of another row. Okay, now all I'm saying there in item 3 is that you can use the addition method, right? Like when we're using the elimination method, isn't this exactly what we're doing? We have 2 equations, and we multiply one equation by a variable, and then we add them together, right? So because you can do that with systems, you can do that with matrices also. Okay, so let's take a look at this example here. What if I had the row operation capital R sub 2 equals -3 times little r sub 1 plus little r sub 2. Okay, a capital R represents a new row and a little r represents an old row. Okay, and I'm going to apply this row operation to this matrix here. So usually we'll make transition arrows, you know, from one step to the next in solving a matrix. Okay, and so here's my original matrix, and I'm going to get a new row 2 by taking -3 times row 1 plus row 2. Okay, row 1 is going to stay the same. Whereas 1, -2, 2. I'm going to get a new row 2. So, let's see, I got to take -3 times row 1 plus row 2. Okay, -3 times 1 is -3, plus 3 is 0. -3 times -2 is 6, plus -5 is 1. And then -3 times 2 is -6. Plus 9 is 3. So this would be the new matrix here that I would have. Okay. Now, when you're solving a system using matrices, the goal is to get the matrix into row echelon form, is what it's called. Okay. And so here's what we mean by row echelon form. Item 1 says that any rows of all zeros are at the bottom of the matrix, right? I know that I can switch any 2 rows that I want. That's a row operation that I'm allowed to do. So if I end up getting a row that has all zeros in it, I'll go ahead and move that to the bottom of the matrix. Item 2 says that for all the other rows, the first non-zero entry from the left has to be a 1. Okay, so if I scan the row from left to right, the first number that I see that's not 0 has to be a 1. Item 3 says that each leading 1 is to the right of all leading 1s in the rows above it. Okay, so let's look at some examples. What if I have these 3 matrices? Okay, all 3 of these matrices are in row echelon form. So any rows of all zeros are at the bottom of the matrix. Here's a row of all zeros. That's at the bottom of the matrix. For all the other rows, the first entry that I see from left to right is a 1, right? So that's what I got there. And then item 3 says that each leading 1 is to the right of all leading 1s in the rows above it. So because I have a 1 here, this has to be to the right of the leading 1 in the row above it. And because this 1 is right here, it has to be to the right of the leading 1 in the row above it. Or in other words, to be in row echelon form, what we're looking to do is we're trying to get 1s down the diagonal and then 0s in the lower triangular part. Okay, now these 2 matrices are technically in row echelon form. Okay, but that's going to be the goal, is to get 1s down the diagonal and 0s in the lower triangular part. So this matrix that we worked with up here, this is actually in row echelon form now. Right, I got 1s down the diagonal and a 0 in the lower triangular part. Okay, now we're going to get some practice solving systems using what's called the Gaussian elimination method. The Gaussian elimination method is just called matrices. Okay, so Gauss was a famous mathematician. He lived about 400 years ago, and he did a lot with matrices and the development there. Okay, so this is, you know, like a lot of books call the method of matrices the Gaussian elimination method. Okay. And the object is to get the matrix into row echelon form. Okay, so we're looking for 1's down the diagonal and 0 is in the lower triangular part. Okay, we'll go ahead and stop the video right there, and then I'll show you some examples of where we're doing that in the next video.